In this session, we are starting a chapter that is chemical kinetics. Chemical kinetics. This is one of the very important and easy chapter, chemical kinetics. Okay, what is the meaning of chemical kinetics? In chemical kinetics, you are going to study rate of a, or speed, you can consider it as speed of a chemical reaction, speed of a reaction, in which speed a reaction is taking place, whether that is spontaneous or it is a reaction is feasible or not, ಒಂದು reaction ಆಗತ್ತೋ ಇಲ್ವೋ ಅದನ್ನ ಯಾವುದರಿಂದ ಸ್ಟಡಿ ಮಾಡಬಹುದು by using chemical kinetics. You will study all those aspects under chemical kinetics. Okay, speed of a reaction, its spontaneity of a reaction can be studied by using chemical kinetics. Speed is nothing but rate of a reaction. Rate. So in which rate a reaction is taking place. So these are the aspects which you will study in chemical kinetics. See, consider you are going, you are traveling in a car. Okay, you are traveling in a car. What will happen if I ask you what's your speed? You will say it is 40 km per hour or 60 km per hour or 70 km per hour, like this. Or if you have not yet started, you will say 0 km per hour, right? You will never say it is minus 10 km per hour or like minus 20, minus 40. You will not say the speed in negative. In the same way, rate can be only positive or 0. Rate can be positive or 0. It cannot be negative. You will not say rate in negative. It will not get negative values. You cannot say speed in negative value. Speed can be 0 or positive. It cannot be negative value. Okay, so hope you understood this. Next, the formula for rate of reaction. How will you find rate of reaction? Rate of reaction can be given by the formula. Rate of reaction can be given by the formula change in concentration of reactant or product. Change in concentration of reactant, change in concentration of reactant or product with respect to time divided by time. As time proceeds, what will happen? Concentration of reactant decreases because they will react and they will convert into product, right? So concentration of reactant decreases, or you can consider rate in the form of product also. Product concentration increases, increase in concentration of product divided by time. I mean, as the time proceeds, reactant concentration decreases and product concentration increases. Okay, you can tell rate of the reaction in terms of either reactant or product. So it will be like final concentration. What will be the final? See, if A is converting into B, okay, so what we'll see to tell rate of the reaction in terms of A, I wanted to know change in concentration of reactant. I should know change in concentration. Change in concentration means what was the initial amount and what was the final amount, difference between final and initial amount. So I can write it like this: final concentration minus initial concentration. Final concentration minus initial concentration divided by time. So this is final concentration minus initial concentration is nothing but change in concentration. Okay, after this is after completion of the reaction, final concentration, and this is in the beginning of the reaction. So what is the rate for this unit for this rate constant? See, in the numerator there is a concentration term. You will tell the concentration term in terms of molarity. So what is the unit for molarity? It is mole per liter. Mole per liter, and in denominator time is there, right? So unit for time is second. Since it is in denominator, if I take it into numerator, I will get second inverse. This is unit for rate of a reaction. So what is the unit for rate of a reaction? Mole per liter per second. It depends, okay. Since your concentration term is in numerator, you will consider mole per liter as rate for molarity, that is concentration, and second time is in denominator. The rate of unit of time is second, so you will take it into numerator and you will get second inverse. There are two types of rate. First one is average rate, and instantaneous rate, average rate and instantaneous rate. See, I am traveling from point A to point B. I am traveling from point A to point B. This is half distance between A and B. Let me consider this as point Q, okay. If my speed from point A to point Q is 40 km per hour, 40 km per hour, okay, till point Q, and from point Q to point B is 50 km per hour. So what will be the average rate? 40 plus 50 divided by 2, you will calculate the average speed, that is 45 km per hour. 45 km per hour is my average speed from point A to point B. Here you will add up all this and you will divide it by how many intervals it is there, like how many kilometers, like that, okay. But in case of instantaneous rate, here you will take average. In average rate, you will take average speed from which you have travelled from point A to point B. I am talking about travelling, but here it is for reaction, okay, average speed of a reaction. Instantaneous rate means I will ask at this point, let me consider it as P. What is your speed at point P? You will say 40 km per hour. 40 km per hour. It is at this particular point your speed is 40 km per hour. This is instantaneous rate. Okay, this is instantaneous rate, and averages you will consider whole thing. Okay, for seeing average rate you will consider whole speed from all the speeds from point A to point B, and you will take average of that. Okay, so this is average speed and average rate and instantaneous rate. Okay, so first let us see average rate. How to calculate average rate? Average rate. See, let me consider a reaction A converting into A gives B. So initially what will happen? A will be in full amount 1. After some time A will start converting into B. Its concentration decreases as time proceeds. Concentration of A decreases. Concentration of A decreases as time proceeds, as the reaction proceeds, concentration of A decreases. So what I will write is decrease in concentration of A, that is dA by dt. Decrease in concentration of A with respect to time can be given, this is rate. Decrease in concentration of A with respect to time, change in time can be given like its initial final concentration at time t2 minus initial concentration divided by final time minus initial time. See, initial I will consider from A to B reaction. A gives B. Initial time is considered as T1 and final time is considered as T2. So initially let me consider A as 1. After some time it will convert into 0. Initially B was 0. after the reaction, after completion of the reaction, B will be 1. So A, concentration of A decreases and concentration of B increases. Here I am taking reactant, that is A. So what will happen to its concentration? Decreases, decrease in concentration of A, that is del A by, sorry, that should be del T. Del A by del T is equal to, so concentration in initial terms, see, you can only check why this is negative. See, in final concentration of A is 0, right? Initial concentration is 1 divided by time. Let me consider as delta T only. 0 minus 1 is minus 1 by delta T. You can see the negative sign here. What this negative sign indicates? Decrease in concentration of A. Concentration of A is decreasing with respect to time. Okay, this is expression for average rate. So you can plot the graph for this like this. As time proceeds, what happens to concentration of A? It decreases. As the time proceeds, concentration of A decreases. Okay, so this is about average speed. Next, sorry, average rate. Next is instantaneous rate. Instantaneous rate. So instantaneous rate means rate at a particular interval of time. See, I am drawing a graph of concentration versus time. So reaction proceeds, concentration of reactant decreases. In a reaction, A converting into B, concentration of reactant decreases. I will ask the concentration, or I will ask the rate at a particular point. At this point, what is the concentration, what is the rate? That gives instantaneous rate. Okay, so see, instantaneous rate can give given by the formula minus dC by dt. You know, this dC by dt represents small change. Okay, small change. At if you will study this in integration, you have already studied this in integration. Small parts can be taken as d by dt. Small parts, you can divide it into small parts which can be taken as d by dt, right, or d by something with which you are differentiating. You can calculate like that. So this small change indicates instantaneous rate. Okay, so as the reaction proceeds, what happened to reactant concentration? Reactant concentration decreases. Remember this. So this is with respect to reactant. If you consider with respect to product, as the time proceeds, what happens? Product concentration increases. So you will get a graph like this. So if I say RA, rate of reaction with respect to reactant, it will comes out to be minus dC by dt, that is decrease in concentration of A, decrease in concentration of reactant. This is for product graph, because as time proceeds, what happens to concentration of product? Concentration of product increases. So A converts into B. As time proceeds, number of B formed will increases, that is concentration of B increases. So what will happen? You will get a graph like this. Concentration increases. This is for product. So in terms of product, rate can be written like this. RB, that means rate with respect to B is equal to dC by dt. Here you will not consider negative sign because concentration of B is increasing. Okay, so this is instantaneous rate. So now let me consider overall rate of a reaction. Overall rate. Overall rate. So what is this overall rate? Let me consider a reaction in which A is giving to B. Okay, this is a general reaction. At time 0, when T is equal to 0, I will take concentration of A as A. Okay, initially B was 0. Since there was no reaction at time 0, no A has converted into B. Now, after some time, so what happened? Some parts of A, let me consider it as X. okay, some part of X is converted into B. So if it is one part of A is one part of A will give 2 part of B. So X part of A will, or X mole of A will give 2x moles of B, right? So what I can write here, x moles of A will give 2x moles of B. So to find the amount of A, I'll write A minus x. This is at some interval of time, after some time. Initially A was the concentration, small a was the concentration of A, and B was concentration of B was 0. After some time what will happen, okay, you can say it like this, I'll consider some number like 5 is the initial concentration of A, and your 0 is initial concentration of B. After some time, let me consider 3 moles of A is converted into B, that will give 6, because 1 mole is forming 2 moles. Okay, so I can write 5 amount of A as 5 minus 3, that is 2. So that is what I have written here, A minus x, which gives 2x. Okay, now wait, rate of disappearance of A can be written like this. Yeah, next is rate of disappearance of A, because as the time proceeds, reactant will disappear, reactant will form product. So I'll write rate of disappearance rate of disappearance of A, because as the reaction proceeds, A will starts disappearing. That means A will be converted into B. So what it will become? Decrease in concentration, delta A by delta T. Since the concentration of A is decreasing, I will write delta A by, this indicates concentration term, okay, delta A by delta T. See, delta A by delta T means initial concentration of A minus final concentration of A minus initial concentration. What is the final concentration? A minus x. A minus x. This is final concentration minus initial concentration. Initial concentration is A divided by delta T. So which is equal to, so decrease in concentration, I have to take minus sign over here. So A will get cancelled, minus into minus is plus, I will get x by T. Okay, I will get x by T in for rate of disappearance of A. Now I will consider rate of appearance of B. Rate of appearance of B, which is equal to del B by del T. So it is in positive, because as time proceeds, product concentration increases. Okay, so del B by final concentration of product, that is 2x. This is final concentration, 2x minus 0 divided by delta T, which is equal to 2x by T. See this, these two equation, x by T and 2x by T. So what it indicates? Rate of appearance of B. Rate of appearance of B is equal to 2 into rate of disappearance of A. See this, this is 2x by T, which is rate of appearance of B, 2x by T, which is equal to, I'll get this after multiplying rate of disappearance of A by 2. If I multiply rate of disappearance of A by 2, I'll get rate of disappearance of B. So I'll write like this, rate of appearance rate of appearance of B is equal to 2 into rate of disappearance disappearance of A, rate of disappearance, disappearance of rate of disappearance of A, which is equal to 2 times rate of disappearance. You have you saw this in your previous slide. See in this slide, rate of appearance of A is equal to 2 times rate of disappearance of A. Rate of appearance of B is equal to 2 times rate of disappearance of A. Okay. Now, so I'll write it like this: rate of appearance of B is equal to del B by del T, which is equal to 2 into minus del A by del T, rate of disappearance of A. Or I can write it like this: minus del A by del T is equal to 1 by 2 into del B by del T. See here, here it is 1 by 1, here it is 1 by 2. I took a reaction, A gives 2B. Here your stoichiometric coefficient of A is 1 and stoichiometric coefficient of B is 2. So in this equation you can see the stoichiometric coefficient of A in denominator and stoichiometric coefficient of B in denominator on the right side. So for a general reaction, I'll consider a general reaction in which A moles of A reacts with B moles of B to give C moles of C plus D moles of D. So overall rate can be given as decrease in concentration of A, that is del A by del T. Here see, I have written stoichiometric coefficient in denominator, stoichiometric coefficient of A in denominator, or I can write it as minus B. In the form of B, I can write it stoichiometric coefficient of B, that is 1 by stoichiometric coefficient of B into del B by del T. Or I can write it in the form of product also, like minus, sorry, it will not be minus, 1 by stoichiometric coefficient of C into increase in concentration of del C by del T. Or I can write it as 1 by D, that is stoichiometric coefficient of D. In terms of D, I am writing this D divided by dt. This is how you will represent overall rate of a reaction. Okay, you will divide the rate by its stoichiometric coefficient. Next is factors affecting rate of a reaction. Factors affecting rate of a reaction. What are the factors which affect rate of a reaction? First one is nature of reactant. Whether it is in gaseous state or liquid state, rate depends on nature of reactant. Different reactants have different rates. It depends on its nature, whether it is large, whether the molecules are closely packed, like that. Okay, whether it is in gaseous state, solid state or liquid state. So depending on nature of the reactant, rate will change. And second one, this is first point. Second point is concentration. See, with increase in concentration of reactant, as reactant concentration increases, what happens to rate? Rate also increases. That means number of molecules participating increases, collision increases. As the collision increases, reaction rate will become high, increases, reaction rate also increases. Okay, and third point is surface area. Surface area. See, smaller the size of a particle or smaller the size of a reactant, greater will be its surface area. If you consider small reactants, then you will get a great surface area, and which increases collision rate. As the surface area increases, collision rate also increases. As the collision rate increases, what happens to rate? Rate also increases. Okay. Next point is temperature. So, as the temperature increases, collision increases. Collision between the particles in kinetic energy increases. Increase in temperature leads to increase in kinetic energy. Increase in kinetic energy leads to fast movement of the molecules, so that and they will colloid more frequently, therefore rate of the reaction increases. Okay. Next is fifth point is catalyst and inhibitors. Catalyst increases rate of the reaction and inhibitors decreases rate of reaction. Okay, these are some of the factors which affect rate of reaction. Next is the rate law. So what it says, what you will get in rate law? See, this rate law gives relation between rate of a reaction. It gives relation between rate of a reaction and rate constant K and concentration of reactant. That may be I will consider at A, concentration of reactant or any reactants. There need not be one reactant always. There may be 2 reactants or 3 reactants, like that. It will give the relation between rate of a reaction, rate constant, and concentration of reactants raised to some powers. Okay, it may be X or Y, anything raised to some powers. Let me consider a reaction. A moles of A react with B moles of B to give C moles of C plus D moles of D. Here I can write rate like this, is equal to K into concentration of A raised to the power X and concentration of B raised to the power Y. Here X and X is order of A, I mean order of reaction or order of reaction with respect to A, and Y is order of reaction with respect to B, and X plus Y is overall order. Okay, overall order, and here K is rate constant. See, here X is order of reaction with respect to A, Y is order of reaction with respect to B. I can calculate overall order by adding these two, overall order of a reaction. This order is purely an experimental quantity. You cannot calculate by theories. Order is purely experimental quantity. Remember this, order of a reaction is experimental quantity. It is an experimental quantity. Order of a reaction is, this is very important, order of a reaction is experimental quantity. It is determined by doing some experiments. Okay, next this rate constant So there are certain characteristics of rate constant. I'll write it over here. Okay, characteristics of rate constant. This rate constant measures the rate of a reaction. It is a measure of rate of reaction. See, if rate constant is greater, rate of a reaction will also be greater. It is a measure of rate constant, this K. Okay, I am talking about K here, rate constant. It is a measure of rate of a reaction, measure of rate of a reaction. If K value is higher, rate constant value is greater, then the rate of the reaction is also higher. Okay, so this value of rate constant is independent of concentration of reactant. It will not depends on concentration of reactant. Value of A will not depends on concentration of reactants. It will not depends on concentration of reactants. See, this value of A will not depends on concentration. If you change the concentration of A or B, that is reactants, the value of K will not change. Okay, its concentration depends only on temperature. It depends on temperature. As the temperature changes, rate constant value changes. Okay, so it will not depend on concentration of reactant, but it depends on concentration of, it depends on temperature. As you increase the temperature, rate constant value also increases, and vice versa. Okay, so next, this unit of rate constant, that means this depends on, rate constant depends on order of a reaction. That this is a constant, it should have some units. Its units depends on order of a reaction. It will have different values for different order. I told you x plus y gives total order. That total order determines unit of a reaction. There are different units for different that means different unit of rate constant for different order. For example, if I consider, if it is a zero order reaction, let me consider a zero order reaction. So this is order of a reaction, and this is unit. Okay, unit for rate constant. Okay, unit for K. I am talking about unit for K. The formula to find unit for rate constant is K is equal to molarity, that is a concentration term raised to the power 1 minus x divided by time. By using this formula, you can calculate unit for rate constant. If x is 0, x represents order of reaction. If x is 0, what I will get? M to the power 1. Concentration is represented in molarity, and its unit is mole per liter, mole per liter, and in denominator time is there, so I will write S inverse. This is for zeroth order. Now if I consider for first order reaction, 1 minus 1 is 0, so m to the power 0 means 1, so I will get only 1 by t. 1 by t means second inverse. So second inverse is unit for rate constant of first order reaction. In the same way, if you calculate for second order reaction, you will get liter per mole per second, and for third order reaction, liter square per mole per second. Okay, this continues. Okay, so you can calculate for second and third reaction by second and third order reaction by substituting the values here. Next is molecularity of a reaction. What is molecularity of a reaction? Molecularity of a reaction. Molecularity of a reaction. Okay, so this molecularity is used only in simple reactions or elementary reaction. Molecularity can be used only for simple reaction. You cannot use it for complex reactions like which is taking place in 2 to 3, 4 steps, or which contains large number of reactants participating in this. You cannot calculate molecularity for that type of reactions. To calculate molarity, the reaction should be simple. It should contain one or two reactant. That's all. Okay. So number of molecules participating in a chemical reaction gives molecularity. So molecularity is nothing but number of molecules participating. Number of molecules participating. For example, I'll consider formation of ammonia. What will happen in formation of ammonia? N2 reacts with 3 moles of H2 to give 2NH3. 2NH3. What is the molecularity of this reaction? 1 plus 3, that is 4. 4 is molecularity of reaction. Okay, there is a difference between molecularity and order. Don't get confused with molecularity and order of a reaction. Molecularity is a theoretical quantity. It is a theoretical quantity, but order is experimental quantity. I told you this, experimental quantity. Order is an experimental quantity, but molecularity is theoretical. I have to calculate by writing the balanced chemical reaction. After writing balanced chemical reaction, you can calculate molarity, but order is purely an experimental quantity. So molecularity can be only whole number. So I cannot calculate half, one, I cannot take half molecule, 1.5 molecule, like that. It should be always in a whole number, molecularity. But order can be 0, negative or positive, or it can be fraction also. Okay, it depends. Okay, experimental quantity can be, order can be 0, negative, positive or fraction, but molecularity will always be a whole number. Okay, next is integrated rate law for zero order reaction. See, I am not going to derive integrated rate law here, or integrated rate equation. Just I will tell you the formula for that. Okay, integrated rate equation for zeroth order reaction. For zero order reaction, integrated rate equation for zero order reaction. So it can be given by the formula K is equal to A naught. This is very important formula, A naught into AT, that is initial concentration of reactant minus final concentration of reactant divided by T. Okay, this is the formula to calculate rate constant of a zeroth order reaction. This is integrated rate equation for zeroth order reaction. To calculate half-life, next comes half-life. What is half-life? It is the time in which reactant will reduce to half of its initial amount. That means half of the reactant will be consumed. See, initially the number of the concentration of reactant is 6. The time taken by this reactant to reach 3, the concentration decreases to 3, half of its initial amount. This time is called as T half. That is half-life. Okay, so at T half, what will happen to concentration of A? Concentration of A at certain time, at this time, this initial concentration is taken as A naught and final concentration is taken as AT. Okay, see what happens here at AT after certain time, that is after T half. When at T half, the concentration decreases by 2, that means half, not by 2, it will decreases by half. Initially it was A naught, I will get 3, that is T half concentration, by dividing initial concentration by 2. Okay, so at T half, AT, that means concentration of A at time T is equal to initial concentration by 2. Substitute this value in this first equation. Substituting these values in first equation, I will get K is equal to A naught minus A naught by 2. I am substituting the value of AT in this equation here. AT is equal to A naught by 2 whole divided by T half. Time T is equal to T half, right? So I'll get T half is equal to, after simplifying, I'll get A naught is equal to 2 times K. Sorry, T half is equal to A naught divided by 2 times K. These two are very important equations. Okay, remember these two equations. This is integrated rate equation for zero order reaction, and this is half-life of zero order reaction. You will get numericals based on these formulas. Okay, next, if you plot the graph, what happens if I for zero order reaction? That means in zero order reaction, rate, and on the time graph, see, rate is equal to K into A to the power 0. If it is A means it is a reactant, so reactant power, its order is zeroth order, so that indicates rate does not depend on concentration of A. So what happens, as the time proceeds, the rate of the reaction remains constant for zeroth order reaction. It will not change. So if I plot the graph of concentration of A versus T, concentration of A versus T graph, see, for this is for zeroth order reaction. What happens, as the time proceeds, concentration of A decreases. So this is initial concentration, that is A naught. This is A naught, initial concentration, and as the time proceeds, concentration of reactant decreases. So slope gives the value of minus K. Slope is equal to minus K. This minus indicates it's decreasing. Okay, so this is how we will plot the graph for zeroth order reaction. There are let me write some of the example for zeroth order reaction, that is 2HI in the presence of AU gives H2 plus I2, or 2NH3. 2NH3 will form N2 plus 3H2 in the presence of platinum PT, or N2O. N2O will form N2 plus half O2. Remember these examples. This is also example for zero order reaction. H2 plus Cl2 in the presence of H nu will give 2HCl. These are all examples for zeroth order reaction. Okay, next is integrated rate equation for first order reaction. Consider a first order reaction, integrated rate equation. Integrated rate equation for first order reaction. Okay, let me consider a first order reaction in which A gives B. Integrated rate equation can be written like this. K is equal to, there is a derivation, I am not going to derive that. Okay, K is equal to 1 by T into 2.303 log of A naught divided by 8. Okay, this is integrated rate equation for first order reaction. So this can be written also in exponential form like this. Exponential form of integrated rate equation for first order reaction can be written like this. AT is equal to A naught into e power minus K into T. Half-life of this reaction can be written as half-life of first order reaction. So it will comes out to be T half is equal to log 2 by K, which is equal to 0.693 divided by K. This is one of the very important reaction. This T half is equal to, so I'll get T half is equal to 0.693 divided by K. This reaction. Remember these two equations. This is also important. Exponential form of first order reaction. and these two. Okay, so here also what happens if I plot a graph of ln A, concentration of A reactant with respect to time, it also decreases like this. Okay, this is the graph for first order reaction. So there are certain examples for first order. Let me give some examples for first order reaction, that is decomposition of N2O5 to form 4NO2 plus O2. This is example for first order reaction. Or H2O2, hydrogen peroxide decomposes to form H2O plus O2, and SO2Cl2 will form SO2 plus Cl2, CH3 CH2 Cl will form CH2 double bond CH2 plus HCl. So these are all examples for first order reaction. And remember this, T 75%, I mean the time in which 75% of the reactants are consumed will be always equal to 2 times T half. The time in which 75% of the reactants consumed is always equal to 2 times T half, and the time in which 99.9% of the reactants consumed is always equal to 10 times T half. Remember these 2 points. Okay, so you will require this in your NEET and CET examinations. Like, you can directly apply in case of some problems. T75 is equal to 2 times T half, and T 99.9% is equal to 10 times T half. Okay, next there comes a step called rate determining step, RDS, rate determining step. Always in a reaction, slowest step will be your rate determining step. For example, it will be like this: A gives B plus C. This is a complex reaction. Here what complex reaction takes place in 2 to 3 steps. Okay, 2, 3, 4 steps like that. B plus C gives D. This is a reaction which takes place in 2 steps. Okay, here if it is a slowest step, then this will become rate determining step. Rate depends on slowest step. Okay, not fast step. Always rate depends on slowest step. Slowest step will be rate determining step. Next one is pseudo first order reaction. Pseudo first order reaction. Pseudo first order reaction. See, in let me take 2 reactants. In that reactant, if I increase the concentration, or if I take one reactant in a very large quantity, then this has no effect on the rate of that experiment, that reaction. For example, I am taking let me consider rate depends on concentration. Rate is equal to A to the power 1 and B to the power 1. Okay, so this is a second order reaction, 1 plus 1, second order reaction. Now what I will do is, I will take B in a very large quantity. I will take B in a very large quantity. For example, A and B are reacting, right? I will take A as 100 and B as 100 and A as 0.0001. See, what number of A reacting with B after certain time, since this is a very small quantity, the reaction will be over. There will be no A, that means there will be no reactants of A left. Only very small amount of B will be consumed in this reaction. So I can neglect that. This is second order reaction, but it appears to depends on only the concentration of A. This B has no effect on this reaction. It has a very small impact on the reaction, so we will neglect that. Okay, so if I take one of the reactant in a very large quantity, what happens? If I take one of the reactant in a very large quantity, what happens? seems to depends on only one of the reactant. See here I have taken B in a very large amount, so it will not, rate depends on only the concentration of A, K into concentration of A. B has no effects. I have taken it in a large amount, so the rate appears to depends on only the concentration of A. What happens as this gets over, the reaction will stop, reaction will not proceed. So only very small quantity of B is consumed, so I can neglect that. So I tell rate depends, appears to depends on only concentration of A. So this is called as pseudo first order reaction. For example, example for this is CH3 COO C2H5, aster, reaction of aster with water H2O in the presence of H plus gives acid CH3COOH plus alcohol C2H5OH. See here H2O is a solvent. I take H2O in a very large quantity since it is a solvent. So I can consider the concentration of H2O as constant. So actually rate should be like this, K into the equation for rate should be like this, K into CH3 COO C2H5 into H2O. Okay, it should depend on concentration of reactant, but what will happen since it water will be present in a large quantity, I have taken water in a large quantity, the rate depends only on concentration of ester CH3COO C2H5. This type of reaction is called as pseudo first order reaction. Okay, it appears to depends on only one of the reactant. Okay, next is collision theory. Next topic is collision theory. Collision theory. For any reaction to occur, that should be mainly three steps, three aspects, not steps. That should be three aspects. First one, molecules should collide. So for a reaction to proceed, what should happen? Molecules should collide. Molecules should collide. Collision should take place. Okay, molecules should collide. A collision of molecules should take place for a reaction to happen. Then there should be sufficient energy in molecule. Molecule should possess sufficient energy. Sufficient energy. Molecule should possess sufficient energy and molecule should have correct geometry. Specific or correct geometry of molecule should be there. So these are the main three aspects for a reaction to happen. Okay, molecules should collide with a sufficient energy and proper geometry. Only the collision of this type of molecules can bring a reaction. Okay, so there is a term called collision frequency, which indicates number of collisions takes place per second per unit volume at given temperature. Remember this, collision frequency. Collision frequency. What is this collision frequency? This is number of collisions taking place per second, number of collisions taking place per second per unit volume at a given temperature. Okay, that indicates collision frequency. Number of collisions will be proportional to concentration of colliding species. As the colliding species increases, that means number of colliding species increases, what happens to collision frequency? It also increases. Okay, so collision frequency is directly proportional to concentration of reactant. As the concentration or number of reactant increases, consider there are two reactant, as the number of reactant or concentration of reactant increases, collision frequency also increases. Okay, so only certain molecules or molecules having certain energy that called as threshold energy, they can only bring about a successful collision or a reaction if the energy of the molecule is below certain threshold energy. Threshold energy. Threshold energy. Molecules having energy above threshold energy can bring about a effective collision or a reaction. If the energy of the molecule is below threshold energy, they will not bring about any reaction. The reaction will not happen if the molecule have energy which is less than threshold energy. Okay, so next is Arrhenius equation, which is given by, this is very important equation. K is equal to, remember this, you require this to solve problems. Okay, A into e power minus EA by RT, where EA is activation energy, that is energy required for a reaction to reach threshold energy or reaction to happen. Okay, EA by RT. This is Arrhenius equation. This is Arrhenius equation. Okay, one of the very important equation. This A is Arrhenius constant, this is rate constant, EA is activation energy, R is gas constant, and T is temperature. Okay, next is temperature coefficient. Next topic is temperature coefficient. So the ratio of rate constant at two temperature separated by 10 degrees Celsius. That should be separated by 10 degrees Celsius. For example, it is a ratio of rate constant. That means there should be two rate constant. I will consider K and KT as rate constant. Okay, it is a ratio of rate constant. Temperature coefficient is equal to ratio of rate constant KT divided by K, which are separated by 10 degrees Celsius. So if K is rate constant at 0 degrees Celsius, KT is rate constant at 10 degrees Celsius, like this. They should separate by 10 degrees Celsius by a unit of 10. This is temperature coefficient. Okay, next is activation energy. I told you EA is activation energy. This is minimum energy, activation energy. Activation energy. This is a minimum energy required for a reaction to happen, or minimum energy required by a molecule to convert into product. Minimum energy. Minimum energy. See, if I plot a potential energy versus reaction progress graph, this is potential energy versus reaction progress graph. What will happen? Initially reactants will be there, they will reach activation energy and they will convert into product. This is for an exothermic reaction. Energy will be released for exothermic reaction. So this is a reactant and here it is product. So this energy is called as activation energy. It is represented by EA, and this amount of energy will be released to surrounding from here to here. This amount of energy will be released to surrounding. So therefore it is exothermic reaction. So in exothermic reaction energy will be released, right? So for endothermic reaction I can write the plot like this. See, this is reactant and this is product. This is also potential energy and reaction progress graph. So here this amount of energy is called as activation energy. Activation energy, and this amount of energy will be absorbed during the formation of product. Okay, absorbed means it is endothermic reaction. So catalyst will decrease this activation energy. So if the activation energy is higher, the reaction will become difficult. I should supply more energy for the reaction to happen. So what I'll do is I'll add catalyst. What catalyst will do? See, initially the activation energy was like this. After adding catalyst, the activation energy decreases like this, or sometimes it drastically decreases. Let me consider without catalyst like this. In the presence of catalyst, it will go like this only. Activation energy, what happens to activation energy? It decreases drastically by using catalyst. Okay, so by using catalyst you can decrease activation energy, so the reaction will become faster. Okay, this is the reason why catalyst increases the rate of reaction. That completes your chemical kinetics chapter. Hope you understood this. If you have any doubts, you can contact me by any time. Thank you.